Okay, everyone, I think we'll get started. Yeah, welcome back. Great, so last week we covered an introduction to reinforcement learning. This week we're covering dynamic programming, which, as I mentioned last week, is sort of the theoretical basis that will underlie many of the algorithms we'll meet. Okay, so last week what did we do? We discussed differences between reinforcement learning and supervised learning. We covered basic elements of reinforcement learning, so these ideas of states, actions, rewards, policies, environments. We covered different types of environments, the distinction between a stochastic and a deterministic environment, different types of state spaces, the distinction between a discrete and continuous state space, and a discrete and continuous action space. We went through a collection of example environments so that you could get a better handle on these distinctions. And then we discussed returns and values. And this week, all we're discussing is returns and values. So this is the topic of this week. And the aim is to have a really good understanding of these concepts and how they work. We also gave a taxonomy of different reinforcement learning algorithms. So what are we doing this week? So we're going to start with a simple Markov decision process, which is finite and doesn't involve any discounting. And we're going to start looking at these ideas of returns, rewards, and values and how they interact in this setting. Then I'm going to give you a set of rules for how you can compute values. So last week we saw some formulas for values, but I mentioned that it's very difficult to actually compute values from these formulas. But there are rules that you can use to compute values in a way that's much more efficient than using these formulas. And we're going to meet those rules today. We're then going to generalize from a deterministic MDP to a stochastic MDP. So we're going to introduce randomness into the environment. Then we're going to introduce discounting. And then finally, we're going to cover a core algorithm called value iteration, which is sort of the classical precedent to deep Q networks, which is the topic of next week's lecture. Okay, let's get started. So this is a MDP. It's a graphical representation of an MDP. You might sometimes see these. So what do the different elements of this mean? So the open circles, these are states. So the initial state of the system is this. Then you can move to one of these two states, then these two states, then these two states, and then this collection of 8 states at the bottom here. The black dots are actions. So from each state, we see that there are 2 actions that can be performed. And we can just think of these as left or right. So in each one of the states, you have 2 actions available to you, go left or go right. What are we missing? What do we need? What's the final element to make this an MDP? Rewards, yeah, right? So let's add these in. So I'm just labeling each one of the, so remember, rewards are administered after an action. So you're in a state, you perform an action, and then you get a reward, and you transition to a next state. So this is how you read this diagram. When I'm in this top state, and I choose the right action, then I transition into this state, and I get a reward of 10, right? Great. So these are the rewards. All right. So first question, is this decision process deterministic or stochastic? So hands up for deterministic. Hands up for stochastic. So it's deterministic because for each one of the actions I can perform, I definitely receive one reward and I definitely transition into another state, right? So if I choose the top, this action here, the one that's closest to me at the top, right, then I'm definitely getting a reward of -1 and I'm definitely transitioning into that state there. There's no randomness in this MDP, it's a deterministic MDP. Is the state space continuous or discrete? So continuous, discrete. Yeah, there's a finite number of states. You can just see them all here. And finally, the action space, continuous, discrete. Yeah, fantastic. It's a discrete action space because from each state, there's only 2 actions you can perform. Fantastic. Great. So we have our graphical representation of MDP. And now what we want to do is solve it. We want to work out how we should act within this MDP to achieve the greatest return. Remember, return just means cumulative sum of rewards. So what does solving mean? It means finding the best sequence of actions. And also as another thing we want to do, we typically also want to find the return for that sequence of actions. So we typically also want to find out like how much reward am I going to get if I make this optimal sequence of actions. So we're going to ignore discounting for now and just treat return as the sum of rewards. So I want to take the path through this MDP that is going to give me the greatest sum of rewards. All right, that's our task. So how are we going to do this? So let's first think of a very simplistic manner for doing this, just so we can work out what is actually the best thing we can do, and then we can check later working against this. All right. So first method is just go through every possible trajectory through this MDP and compute the return that I'm going to get from that trajectory, right? So I might start at the top and then go left and end up here, and then go right, and then go left again. And this is one trajectory through this MDP. So these bottom states here, these are terminal states, and when I hit these, it's over, the game is up, right? And then I can consider all possible routes through this. And this will tell me all the possible things I could do, and from this I can work out what the best possible thing to do is. So how many different paths are there through this MDP? How many trajectories do I have to consider? Yeah, 8. So there's 8 terminal states, and each path uniquely leads to a terminal state. So there's 8 different sequences I can consider. So let's compute the return for each one of these different ones. So for this one closest to me, I've got -1, then 7, so 6, 15, so 21 of return, right? For the one furthest away, it's 10, 2, 4, so 16 is my total return. Does this make sense so far? Okay, so from looking at this, we can instantly see what the best trajectory is. It's this one here with 22 beneath it. So my best possible choice of actions is to first go right, then left, and left again, and I'll end up here. All right? Okay, so let's note some things about this MDP that are kind of interesting. So first of all, the trajectory with the highest return involves taking the locally worst action twice. What do I mean by this? If I'm at the top and I only see the returns I'm getting from the reward I'm getting from the immediate action I take, then it's very clear I should take this action here, which gets me a 10. But the actual optimal action to take is the one that gets me a reward of -1 immediately, because it puts me in this state, and this state is in some way better than this state. And so the loss of reward I get from taking this action is made up for by the fact I end up in a better state. And so this is going to motivate what happens later when we see that when considering how good something is, we need to consider both the local reward we're getting and how good the state that we end up in is, right? And this happens again here. So when I'm at this node, the locally best action is this, or the locally highest reward action is the one that gets me a 7, but the one I actually want to take is the one that gets me a 3, because that's the only way I can get this 22 down here, right? So this is recapitulating something we met last week, which is in reinforcement learning, we need to consider the long-term consequences of our action, not just the immediate rewards that we're getting. All our decisions are coupled, and we need to take action so as to put ourselves in a position to obtain a high reward at a later date, often. And if you take the locally best action, you can actually end up with very low returns. So I go 10 and then 5, then this 14 and this 15, these are the lowest possible returns that I can get across all possible nodes. So this greedy approach of just pick whichever action gives me the greatest reward definitely doesn't work here. It results in the worst possible play that you could, or second worst possible play that you could possibly have. Okay, so we've met one method, which is enumerate all these trajectories. And now we're going to introduce another method, which gives us a more powerful conceptual framework to work with that's going to come in useful when we want to move to these deep algorithms. So this method is dynamic programming, which is the topic of today's lecture. So the way dynamic programming works is that we're going to find the value of each action. So we met values last week, and I want you to temporarily take that concept of values that we met last week and put it aside. I'm going to reintroduce the concept, and then eventually, and I'm going to build that concept up, and eventually the two will meet again. But for now, I need you to maintain like a separate concept that we're slowly going to build up in this lecture. So what do I mean by value of an action? So optimal trajectory is just going to be the trajectory that chooses the highest value action at each state. So I need this value to encompass not just the local reward that I'm going to get, but also how good the state that I'm moving into is, right? That's what this value has to accomplish. That if we've seen that if I choose actions so as to maximize reward, the immediate reward, then I'm going to get very bad play. And so I need something that I can maximize that's going to result in good play. And that thing that I can maximize that results in good behavior is value, because value is going to encompass not just the local reward, but also the value of or how good the next state that I'm going to move into is. So how are we going to do this? So optimal decision making involves considering the entire future trajectory after taking an action, right? I'd need to not just choose actions that lead to high reward immediately, but actions that are going to generate a good trajectory in the long term, right? So we know the future at terminal states. At a terminal state, the future is nothing, right? I'm done. That's the end of the process, right? So I want to be able to compute things about the future, and I know the future at terminal states. And so what I can do is I can start with the fact that I know the future at terminal states, and I can sort of recurse backwards. I can build backwards from those terminal states to find what's going to happen in the future from any state. So these are some intuitions. We'll get into like the maths of how you make this work. But the core idea is that value information about how good something is, not just locally, but completely, this flows backwards, and it's going to flow backwards up the MDP. And it's going to start at these terminal states where we know the value, and then we're going to work backwards from them upwards. So value to us is going to mean the return, so the sum of rewards, assuming optimal decision making. So I'm at some particular state, and I want to know what the value of an action is. And what I mean by that is how much return am I going to get? So what's the sum of rewards I'm going to get from that action if I then can continue to play optimally from that point onwards? Yeah.
Why would you assume optimality in the subsequent steps rather than assuming your current policy?
So if you assume optimality in the current steps, then you'll find out what is better for you to do, assuming you then continue to behave optimally. And if you have the values, then these tell you what optimal behavior is. And so all you need to do is just continue to follow the values. Yeah.
So by optimal decision making, just means selecting the highest value.
I mean selecting the action that's going to lead to the highest return overall, right? So at each state, I consider the action values of that state, and those action values are just the cumulative sum of rewards I'm going to get from that action onwards, assuming I just continue to behave optimally, continue to make the best possible choices I can. So the return for an action, so the cumulative sum of rewards, can be decomposed into immediate reward, so what I get immediately after performing the action, and then all of the rewards after that point. Does this concept make sense? So return is sum of all future rewards, and all future rewards can be written as immediate reward plus all the rewards after that. And this decomposition is what's going to allow us to compute these values. So the value of an action, how good an action is, can be decomposed into the immediate reward I'm getting for that action. So immediate reward plus the value of the state that I end up in. Okay? All right, so currently I've told you some things about values, I've given you some intuitions. Now let's make it rigorous and see how we can apply it to this MDP. All right? So now I'm going to introduce some rules that we can use for computing values that are based on these different intuitions. Okay, so rule 1, terminal states have 0 value because there are no future rewards. So as I said earlier, we know the future at terminal states. At a terminal state, there is no future. We're done. And so we know the value of terminal states. The value, remember, is just the rewards I'm going to get, assuming optimal play from this point onwards. But if I'm at a terminal state, I'm getting no more rewards. there is no future, I don't get any more rewards, and so the value must be 0. So this is like our first axiom of how you compute values. All right? At terminal states, there is no more value. Okay? The second axiom is what we call the principle of optimality. And this says that if I'm at a non-terminal state, so I'm at any state that's non-terminal, the value of that state is the maximum value of all the actions I can take off that state. And this is precisely that part about assuming optimal play. So if there's two different actions I can take that have different values, what's the value of being in this state? Well, I get to pick what I do, right? If I have these different actions available to me and I get to choose between them, I'm going to choose the one that has the highest value. And so the value of the state is then just going to be the maximum value of the actions off that state. All right? This is the principle of optimality. This is our second axiom. The third axiom is that the value of an action, so the first two about values of states, they tell us if I'm at a terminal state, the value is 0. If I'm at a non-terminal state, it's the maximum action value. So all we need now is to know how to compute action values. This is what our third axiom is going to do. And this says that the value of an action is the immediate reward I get plus the value of the state you transition into. All right? And that's precisely this part here, that the value of an action is the immediate reward plus the value of the next state. And this comes from the fact that the return from an action is the immediate reward plus the return from the next state. All right? So all I'm doing here is moving from returns into values. Okay. So I think this hopefully will become more clear once we've worked through an example and computed values. So yeah, terminal states have 0 value. So the value of a terminal state is 0 if S is terminal, right? So the previous axioms were given in sort of verbal format. Now let's write down the equations that express these in maths. So terminal states have 0 value. All right, this is our first axiom. The second axiom is that the value of a non-terminal state is the maximum value of all the actions off that state. How do we express this mathematically? The value of a non-terminal state is the maximum over actions from that state of the action values at that state. Right? Second axiom. And finally, the value of an action in a state is the immediate reward for taking the action plus the value of the next state. So to express this mathematically, we have Q star SA equals R plus V star S prime. So these are all the axioms we need to know at this point for computing values. There was a question.
So for the value, is that just one, are you just considering one step? Maybe you want to consider two steps?
Yeah, so you can, these are sort of recursion relationships among values. This is how we can think of them. And you can just unfold these 2 steps or 3 steps into the future. Yeah. So at the moment, we're considering these sort of one-step relationships where the relationship between where a state is put in relationship to all of the actions off that state, and an action is put in relationship to all the next states off that. And so these are one-step relationships. But yeah, you can generalize these to multi-step relationships. Okay, so these are axioms for computing values. Now let's apply this to an MDP, and hopefully this will help some of these concepts click. All right, so this is our MDP again. So the open circles are states, the black circles are actions. And now we're going to compute the value of every state and every action in this MDP. So how are we going to do it? Well, remember one of the key intuitions I gave was that value information flows backwards. So which state are we going to start computing value information at? Or which states will we start computing value information at? Anyone? Yeah, the bottom, right? These terminal states. The terminal states are the ones where we're going to start computing values, and the value information is going to flow backwards in time up this MDP. So I have all these terminal states here. What's the value of each one of these terminal states? 0, right? The value of a terminal state is 0 because there's no more reward to have from that point onwards. All right, so all of these get value 0. So now we're going to flow backwards. So let's look at actions that lead to that state. So what's the value of this action here? Okay, any guesses? So the action closest to me. Not 6, someone else? 15, right? Because the value of an action is the immediate reward I get, 15, plus the value of the next state, 0. So this action here has a value of 15. And the same goes for all of the other actions I have. All the other actions, their value is the immediate reward they get, plus the value of the next state. The value of the next state is always 0, so it's just the amount of reward. And so what does it mean that this action here, so the action furthest from me, what does it mean that it has a value of 4? What does that mean? It means that if I take that action, the total amount of rewards I'm going to get from that point onwards is 4. All right? Okay, let's move on. So the next thing we're going to do, remember value information flows backwards. So the next layer are these sort of second tier states, the ones that are going to lead to those actions whose values we just computed. So the state that's closest to me, what is its value? 15, right? Because the value of a state is the maximum over the values of the actions off that state. Yeah, there we go, 15. What does it mean that this state has a value of 15? It means that if I'm at this state and I play optimally, the total amount of return that I'm going to get from that point onwards is 15. Because if I'm at this state, I play optimally, which means I take the action that's closest to me, and then I get a reward of 15. So the total amount of future reward is just 15. Okay? Okay, next node. So this node here, what's the value of this state? 20, right? Because if I'm here, then I should go this way. I should take the action on the left, and then I'm going to get 20 reward, right? And the logic continues for the other two, right? So we're starting to see now how we can apply these rules to compute these values. Okay, we're going to do like one more, and then I'll stop belaboring the exercise. So this action here at the next level up, that's closest to me, what is its value going to be? This is slightly harder. Take a minute to think. Okay, any guesses? 22, right? Because if I'm at this action, remember the value of an action is the immediate reward I get, which is 7, plus the value of the next state, which is 15. So the value of this action must be 22. What does it mean that the value of the action is 22? It means that if I take that action and I then play optimally from that point onwards, I'm going to get 22 reward total in the future, right? I'm going to get 7 reward then, and then I'm going to get 15 reward here, right? What about the next one? So the next node over, what's the value of this node? Yeah, because I'm going to get a reward of 3 from the immediate transition, and then I'm going to transition into a state that has a value of 20. And so the total value is going to be 23. All right, let's just, yeah, so I take the maximum here, 23, take the maximum here, 10, and then I do the backups here. So 23 minus 1 gets me 22, 10 plus 10 gets me 20, and then finally the top state, 22. So what does it mean for the initial state to have a value of 22? It means that if I'm at the initial state, the maximum return that I'm going to get is 22. And look, this is correct, right? The maximum return I can get from any of the trajectories is indeed 22. We already found that out earlier, right? Okay, what else can I do with action values? Well, it's clear now that I can use these action values to guide my decision making. So I'm at this initial state and I want to know which action shall I take? Well, this action has a value of 22 and this has a value of 20, so I should take the action with value 22. I take it, I transition to this state. Which action shall I take then? Well, I should take the action with value 23. I transition to this state. Then which action shall I take then? I should take the action with value 20 and I transition to this state. And this gets me 22 reward. And this is the optimum trajectory through this, which we computed at the start. We already found this optimal trajectory, and we can see that optimal behavior just means at each point I maximize action values, right? And this is what makes values different from rewards, that we saw that if at each point I maximize reward, I actually end up with a trajectory that isn't good at all, right? But if at each step I maximize value, then I end up with the best possible trajectory. So values are encompassing not just local rewards, but everything that's going to happen in the future into a single number that I can then use to guide decision making. All right? Yeah. Let's just pause here. Does anyone have any questions? Covered a lot of stuff already. Yeah. Yeah. So we're gonna see in like 2 slides. So in the case where the environment is deterministic, then there isn't much difference in the computational complexity. But when the environment gets stochastic, it then becomes much harder, because then every single trajectory not only has we not only need to consider like the trajectories, but also the probability of each trajectory. And this becomes a much harder thing to just brute force. It also becomes much harder to just brute force search through trajectories when the environment contains a loop. So in this case, this MDP, there's no loops in it. There's no way that you can go back to where you are. And we'll see that dynamic programming still works like really well when your environment has a loop, whereas brute forcing, like search through all possible trajectories through the environment, works less well when your environment contains these loops that circle back to themselves. Yeah, okay, great. So, I now want to introduce to you this Bellman optimality equation. This is the equation that we used for, or this is like a synthesis of these different axioms. So remember, this is our second axiom, right? Oh, sorry, our third axiom, that the value of an action is the immediate reward I get plus the value of the next state that I transition into, right? This is axiom number 3. Then let's combine this with axiom number 2. So axiom number 2 was that the value of a state is just the maximum of the action values of that state. All right? So here I'm using A prime to denote next action, just as S prime denotes next state. All right? So this is axiom number 3. This is axiom number 2. And now I just need to put these together like this. Right? So this gives me a relationship between action values that doesn't make reference to state values. And this equation here is called the Bellman optimality equation. And it's going to form the basis of DQN, right? With some modifications. But yeah, this is the sort of basis of DQN. And it tells me that the value of an action is the immediate reward I get for that action, plus the maximum value over actions in the state that I end up in. All right? And it's obtained by literally just putting together these 2 equations here. Okay. Yeah, value of an action in a state, immediate reward, the value of the action in the next state, and this is the assuming optimal action. So this is the optimality part of it, the fact that I'm taking a maximum over next actions. I'm assuming that I'm going to take the optimal action. All right. Does anyone have any questions? No? Okay, fantastic. Oh, yeah. All good? Cool. So we've covered a finite MDP without discounting that is deterministic. And now we're going to take this and we're going to move to a stochastic MDP, and we're going to ask, like, how can we modify the rules that we have to deal with stochasticity? All right, that's our task now. So we know how to compute values when the environment is deterministic. Now we need to know how we're going to compute values when the environment contains randomness, when there's stochasticity in the environment. So consider this MDP. So once again, white nodes indicate states, black nodes indicate actions. And this MDP, as you'll notice, is stochastic. What I mean by that, if I take the action on the left here, and I take this action, then there's a chance of transitioning to each one of these next states. And so we need to annotate this with both the rewards and the probabilities of those transitions. So when I take this action here, right, on the left, I have a 50% chance of transitioning to this state and a 50% chance of transitioning into this state. All right? And when I take the action on the right, there's a 2/3 chance of going this way and a 1/3 chance of going this way. So now I need to generalize my methodology to take into account the fact that there's something uncertain that I don't know about what's going to happen in the environment. Oh, yeah. So we're going to assume that we have all these state values here. So we've assumed that we've run the backup all the way up the tree up until these states here. And then we're going to ask, how are we going to compute the value of this state here and the values of these actions? All right? So we run this backup, and these are the values that these different states have. So 4, 3, 3, 0. All right? These are the values of the different states. Okay, so let's take a moment and as a problem, which one of these two actions do you want to take? Think about it. You're in this state. Do you want to go left or do you want to go right? I'll give you 10 seconds to think about it. Okay, so hands up for going left. Hands up for going right. Okay, so this proves to me that you all have a very intuitive grasp of what the rule should be. So let's just write out what the rule should be. So suppose I'm going left. Well, there's a 2/3 chance that I get a reward of 2 and then a value of 4. And so I should be 2/3 2 plus 4 plus a 1/3 chance that I get a reward of 0 and then a value of 3. And so if you write this out, this means that the value of this action is 5, right? And so we can immediately see what the intuitive rule is for when there's randomness in the environment. I take a weighted average of the futures weighted according to the probability that they happen, right? What about the other one? Well, the value for that is 3. Why? Because it's half of 4 plus a half times 2, the 2 plus 1, 3, all right? So we all already intuitively understand how you compute values for stochastic environments. Oh, and then the value of the state will just be 5 because it's the maximum action value. Wonderful. So this means that in a stochastic environment, the rule for an action value becomes action value is sum over all the transitions I could experience, all the things that could happen after taking that action, of the probability of that transition times reward plus next state value. All right? And this is very intuitive. You all grasp this immediately. Okay, so what's the Bellman equation look like in stochastic environments? So in a deterministic environment, this is our Bellman equation. Action value is reward plus maximum over over actions of the next state. Okay, for a stochastic environment, the Bellman equation is just going to have this expectation here. So this is an expectation of R and S prime, so reward and next state, given that I'm in a certain state and I perform a certain action. Does that make sense? So I condition on being in a certain state and performing a certain action, and I'm going to take an expectation over all of the transitions I can experience, or the reward and next states that I can end up in. All right? And remember that the value of a state is just the maximum of the action values over that state. So this can also be written as expectation of R plus V star S prime, if you like. Another expression for this Bellman optimality equation. This is for stochastic environments. Okay, so we're averaging the reward and next state over the dynamics function. All right? And that's how you deal with stochasticity. Okay, great. Any questions at this point? I feel like everyone understood that very well. Yep.
Seems like you wouldn't care about the expected value and not the variance of the value. Perhaps if you have huge variance, so the expected value is big, but we never see it.
Yeah, so the question was about do we only care about expectations and not variances? And the answer is, like, in general, yes. However, there is a branch of reinforcement learning called distributional reinforcement learning, where you aim to capture not just the in expectation what happens, but the entire distribution over what could happen in the future. And you aim to try to learn this. And in this field, sometimes they have like decision rules where you take into account high variance actions. And you specifically choose actions that have you penalize actions according to their variance. But in classical RL, which is what we're studying here, we literally do only care about rewards. Our aim is maximize expected reward or expected total reward. We don't care about variance. Yeah. Okay, so we've generalized to the stochastic setting. Now we just need to generalize to the discounted setting. Okay. So I introduced this idea slightly earlier. But what happens when our MDP has loops? This is actually like extremely common. It's like very common to be in an environment where you can do a sequence of things and end up back where you started, right? If you're a mouse running around a maze and you do, up, down, left, right in sequence, you will end up back where you start, right? So what are we going to do when an environment has loops? So why does this case need to be treated separately? Well, consider this environment. So I start in this state, and then I have two actions. This action gives me a reward of +1 and transitions back to this state. This gives me a reward of 0 and transitions into this state, which has a value of 5. So that you can consider there being an entire other MDP that's down there we're not looking at. If I back that all up, this has a value of 5. What's the value of being in this state? Have a think for a moment. Any suggestions?
As much as you want.
Yeah, infinite, right? The value of being in this state is infinite because I can just run around this loop as many times as I want, accumulating more and more and more reward, right? And so in this case, it's very simple because there's a loop that's like of length 1. You just immediately loop back to yourself. But in any environment that's deterministic and has loops where you can accumulate positive reward around that loop, you're going to run into the same issue, that I'm going to have states that has infinite value. So what's one way that we can get around this? Well, one way we can get around it is say that, the value being in the initial state is infinite. So one solution to this is to discount rewards in the future as compared to the present. So I say if I'm in this state, it might be that I can run around this infinitely many times. But for each one of those future loops, the reward I'm going to treat that loop as having, so the effective reward in value computation, is going to go down by a factor of gamma, right? And this will result in this state having finite value, which is very useful because it means that we can run algorithms on this. We can't run algorithms on something if it just ends up having infinite values. Or like we need to run very different types of algorithms from the ones that we've been talking about already. So we want to unify everything and put it in one framework. So discounting, let's sort of remind ourselves of how this works. The return, I'm going to redefine it as the discounted sum of future rewards. So now I'm going to introduce this discount factor where for each time step I go in the future, I'm reducing the reward by one discount factor. So how does this get expressed mathematically? It's the reward I get from the first step plus discount factor reward at the next step plus discount factor squared reward at the next step. And we see that every time step I go removed in the future, I pick up another discount factor. All right? And here's a mathematical way of expressing it. Don't worry too much about this, but if you want it, it's there. So every time we take a time step, we multiply all future rewards by a discount factor that is below 1. All right, how does this help? How does this solve the problem of loops? So suppose that I just keep going left infinitely. Like I always choose this, and I keep going round and round. I want to know what's the return, i.e. discounted sum of rewards I'm going to get from doing that, from just keeping going round and round and round. So the sequence of rewards is just going to be 1, 1, 1, 1, on and on forever. All right. So my return is going to be 1 plus gamma times 1 plus gamma squared times 1 plus gamma cubed times 1 plus gamma to the 4 times 1, where at each time step in the future, I pick up another discount factor. All right? Everyone follow? This is just the sum of 1, gamma, gamma squared, gamma cubed, on and on like this. And if you've met this before, this sum converges, which means that it eventually reaches, it never reaches, but it gets closer and closer and closer to a finite value. And that finite value is 1 over 1 minus gamma. So by introducing this discount factor, this state has gone from having an infinite value to a finite value of 1 over 1 minus gamma. Now, this is just like a toy example where I've got this loop, but as a general statement, if I'm in an environment and I have a discount factor and the rewards are bounded for the environment, so there's no transition I can take, that there's a finite maximum reward or minimum reward that I could get for any given transition. So I can't get like rewards of plus 100, 200, 300, 400, and on like that. If my rewards are bounded and I have a discount factor, all values will be finite. So it's going to make sure everything's finite, and this is very useful for computing values and things, because we don't end up with these infinite blowups. There's another reason we use discounting. This is sort of one justification you hear very often, which is that it makes everything finite. We're going to see another justification, which I think is like far more intuitively appealing than this at the end of the lecture. So if you're like still a bit confused about why don't we just care that this has infinite value, then stick around and we'll sort of cover another motivation at the end of the lecture. So the bottom line is discounting ensures that all returns and values remain finite. All right? If you didn't follow this argument, don't worry about it. The important part, the bottom line is it's going to ensure everything's finite. And this is very useful for us. Is there a question?
May I ask if we put for this polynomial, if
Yeah.
we put the 5 there and we put the 1, and if in that case they just keep discounting, and the system will still think it's better to remain with it. And in that case, it's still infinite.
So the actual amount of reward that it will get is infinite. It will just keep going down the loop, but the value will be finite. And this is useful because we want to compute values. And if we start getting infinite values, it's going to make things like tricky later down the line. So one reason it would make things tricky is if I can have an positive infinite value, I can also have a negative infinite value. And then imagine I'm at a state, right? And I've got the option of doing an action that has a positive infinite value. Oh, sorry. There's an action I can perform off a state. There's a 50% chance of transitioning into a state with positive infinite value, and a 50% chance of transitioning to a state with negative infinite value. What do I do? Is that a good action or not? There's no way to know, right? Like, I can't just add up positive infinity and negative infinity. So if everything's finite, it means everything plays well together, and I can continue using all the rules that I've got. But you're entirely correct that if I do this, and I just keep going, if I run my agent, and it does just keep running around this, it will accumulate an infinite amount of reward. But this is distinct from the problem of how do you compute values, all right? So this is like a computational trick. The discounting, I would encourage you to conceptualize it as a computational trick that we use that keeps things finite and also is going to allow us to do some other stuff a little later on. Okay. So we're gonna just perform some manipulations on this. So my return is my future discounted cumulative sum of rewards, right? Okay. All I'm going to do is I'm going to pull this discount factor out of all of these, right? So all of these terms, all the future terms past the first one, have the initial discount factor plus times some additional number of discount factors. So I can pull one discount factor out of all of those terms. So I have discount factor, and then I have all of these future terms. But now let's have a look at this. This is RT plus 2 plus gamma RT plus 3 plus gamma squared RT plus 4, and on like that. And this is just going to be the return at time t plus 1, right? Because if I take this equation and I exchange t for t plus 1, I get precisely what's in these brackets here. So this gives me a recursion relationship among returns, right? It tells me that the return at time t is the immediate reward plus discount factor return from all future time steps past that. So this is a recursion relationship that exists among returns. Gt equals RT plus 1 plus gamma Gt plus 1. Return, immediate reward, discount factor, next step return. All right? Does this make sense to everyone? Does anyone have any questions about this? Okay. So why is this helpful? So we have this relationship, return is immediate reward plus discounted next step return. We know that the value is the expected return, right? we introduce this at the start. Values are just expected returns. And we can see how this motivates, it's not a proof of, but it motivates the following relationship among values, which is that the value is going to be the expected immediate reward plus discounted next step value, right? So this is our new Bellman optimality equation, right? We've met the Bellman optimality equation for the deterministic setting. We've now met it for the stochastic, where we just introduce this expectation. And now we're generalizing to the discounted setting. How do we do that? All we need to do is say, well, when I'm considering next step values, I pick up a discount factor of gamma, all right? So the only new thing is that I pick up this discount factor of gamma when I'm transitioning into the new state. Because in the transition into the new state, I'm one step away. The new state S prime is one step away, and so I pick up one discount factor for that, right? So this is our Bellman optimality equation in the discounted setting. And it comes directly from this relationship here. It's like this relationship, but I'm like applying expectations in a certain way. Okay, great. So we now have our Bellman optimality equation. I'm going to give you here, but not go into a whole lot of detail for, like, I will motivate, but not go through the entire proof that we just went through for the Bellman optimality, Bellman equations for other policies. So what we've met is the Bellman equation for the optimal policy, for optimal play, right? And the optimality comes from this maximum here, right? So in asking, like, where here am I assuming that I'm pursuing an optimal policy, the place I'm assuming that optimality is the fact that I'm taking a maximum over the actions I could take. This maximum over actions is implicitly an optimal policy, right? But now, what if I want to compute values when I'm not performing optimally? What if I have some fixed policy I want to pursue, and I want to know what's the value of the different actions and states under this policy, all right? Okay. So let's start with, okay, so this is the standard Bellman optimality equation, right? Expectation, reward plus gamma, next state value, where I'm taking a maximum of the actions. So what if I have a deterministic policy? So maybe take just a moment and think in your head, how would you modify this relationship if instead of pursuing the optimal policy, you're pursuing a deterministic policy? So just think for a moment. All right. Yeah.
Without the probability step. So without the S, the expected value without probability of the Q star.
So we still have this conditioning on S and A. This isn't the part that we're going to change because in computing action values, I am always conditioning on taking a certain action. I'm always saying, what happens if I take this action? So there's another part of the equation I need to change. Anyone want to guess? Yeah? Yeah, right? So this maximum is encoding optimality. It's encoding the optimal policy. But if I know that I'm not performing the optimal action, but I'm going to perform the action mu of S, then what I should have here instead of A prime is mu of S prime, right? So this is our Bellman equation for a deterministic policy, where I say the value of taking a certain state, of taking a certain action in a certain state, is the expectation over transitions, conditional on that state action pair, of the immediate reward plus discount factor, the value of being in the next state. What's the value of being in the next state? The value of being in the next state, this term here, is just the action value of being in that state and taking the action that I know I'm going to take, which is mu S prime. That's the action I know I'm going to take. So the state value is just Q S prime mu S prime. All right? Anyone have questions about this? Yeah.
Why do we still have expectation? Because from before you said Bellman equation in deterministic, we have expectation, right? And then when we switch to stochastic, this becomes expectation.
Yeah. So the question was, why do we have an expectation? The reason is because our policy is deterministic, but our transitions are not. So the environment is in general a stochastic environment. And so the expectation here is not an expectation over my behavior, but is an expectation over transitions that occur following the state action pair. So I'm averaging over dynamics, not over my own behavior. Okay. What about a stochastic policy? So again, just take like a few moments to think. Remember, the only thing I need to do is take this bit part here, which is the next state value, and replace it with what should the next state value be if I'm following a random a stochastic policy like this. I'll give you 10 seconds. So for a stochastic policy, the value of the next state is just the average of the action values under my policy. So what does that look like? Again, I'm averaging over dynamics here, reward plus gamma. This is all the next state value. Let's unpack that. The value of being an S prime is the value of being an S prime and taking action A prime weighted by the probability that I take A prime, and then summing over all these actions. Does this make sense? Yeah. So this is our Bellman equation for a stochastic policy. So these other two, deterministic policy and stochastic policy, we're also going to use them. For DQN, we're going to be using the Bellman optimality equation. Okay, great. Any questions at this point? Otherwise, let's try to push through for the final part of the lecture. Fantastic. Okay, the last thing we're going to do is introduce the value iteration algorithm, which, as I said, is going to also give another meaning to the discount factor and another way of understanding it and interpreting its role within reinforcement learning. So, the key idea of value iteration is that the Bellman equation, any Bellman equation, can be used to turn value approximations into better value approximations. So in all the equations that we've met so far, we're relating the actual values of things, right? The actual value being in a certain state, the actual value of taking a certain action. But in general, we don't know these. We have approximations to them. So the question becomes, if I have an approximation, how can I make it better? How can I improve my approximation? And value iteration is one way of doing this. It's a way of turning a value approximation into a better value approximation. This idea that you can take an approximation and use it to form a better approximation is called bootstrapping, right? Because you are building off something that's an approximation to get a better approximation. And we're going to be using bootstrapping a lot. It's like one of the key ideas in RL. Bootstrapping is when I form an estimate of value from an estimate of value. So I have an approximation, and I'm going to form a new approximation from that is better in some way. All right? So these are all just expressing like the same core idea, right? So I'm taking my existing approximation and I'm moving to a better approximation. So this is my Bellman optimality equation. This is relating the actual optimal action values, right? So these are the actual optimal values, all right? What happens if I just have an approximation to this? So I have a current approximation to optimal values, which is Q old, right? This is my current one that I've got. I want to make it better, right? I want to make Q old better, all right? I'm going to form a new approximation by turning this equation into an update rule. How am I going to do that? I'm going to say the new value approximation will be this, where I plug in my old value approximation for Q star. So the update rule looks like this. My new value approximation is equal to the expectation of the rewards plus gamma, maximum over actions, of the old action value function. All right? So this is no longer an equation. So this is an equation that relates Q star to itself. It's a recursion relationship that allows you to relate the value of some actions to the value of other actions. All right? This is not an equation. This is an update rule, right? It tells me if I have Q old, how do I get a better Q? How do I get Q new? So this is an update rule that I form from this equation. And value iteration is just going to repeatedly apply this update rule. So we are going to take our Q. Yeah, let's just walk through this. So I start with an initial Q function. Let's say that this is just like 0 everywhere. I have no idea about anything, so I'm just going to set all action values to 0, right? And then I'm going to form a new approximation according to this rule. So my new value function for any state action pair will be equal to the expectation of reward plus gamma maximum over old of this given S and A. Now initially Q old is always 0, so it's just going to be these rewards. And then that's my new value function. And then I'm going to plug it back into this equation. So that then becomes Q old, and I'm going to get a new version by plugging it into this, right? So I can keep iterating this over and over again. And this is why it's called value iteration, right? That we repeatedly apply this rule, and each step we make Q new into Q old, and we just keep iterating like this in a big loop, all right? And the claim that I made is that every time I apply this loop, every move I make along this loop is going to improve Q new, right? It's going to make Q new better. In what sense is this true? So in what sense is Q new a better approximation? So it's better in the sense that if I keep applying this procedure, if I keep setting Q new equal to Q old that, and then iterating through, I keep applying this update rule again and again and again, I will get as close as I like to the optimal action value function. So we can approximate it arbitrarily well. And if you do this an infinite number of times, not that you ever can, you actually get there, right? You actually get to Q star. In the limit, as you perform this procedure an infinite number of times, you reach the actual optimal value function. And that's the sense in which it's better. Okay, so I think this is the last slide, hopefully. And it's going to run through an intuitive argument for why value iteration works. This is not a mathematically rigorous argument, but it has the exact form of the mathematical argument. And so if you want to know why it works mathematically, it should be easy to follow if you can follow this argument. So this is my update rule that relates my new value approximation to my old value approximation. And I'm going to say that my old value approximation is equal to Q star, right? The actual thing I'm trying to approximate, plus some error. And this is my old error, right? So what I'm saying here is that this is an approximation, right? This is the thing I'm trying to approximate plus an error, all right? So let's shove this into this update rule here. So Q new is equal to expectation over transitions, reward plus gamma, and then this is encompassing maximum over A prime of Q old, which is just Q star S prime A prime plus error old, right? So all I've done here is I've taken this equation and I've plugged it into this one, right? Second line plugged into the first. All right, now let's expand let's distribute gamma over terms, and I'm going to get this, right? Q new is equal to expectation reward plus gamma maximum over actions Q star S prime A prime given SA plus gamma error old. All right, everyone with me so far? What I've done is I've pulled the gamma out, and then I've also pulled the error old outside the expectation. This is this is a very hand-wavy argument, so don't get too caught up on why it's fine to do that. Okay, but then look at this thing here, right? This is just Q star SA. Why is it Q star SA? Because of the Bellman optimality equation. The Bellman optimality equation tells me precisely that this expectation is just Q star SA. So the final line I have is my new approximation is equal to Q star SA plus gamma error old. What does this tell me? This tells me that my new error is gamma old error, right? I know this was a very hand-wavy argument, but hopefully you follow this, right? What does this mean? It means that every time I apply value iteration, every loop of this process I go through, the error term goes down by a factor of gamma, right? Remember, gamma is between 0 and 1. Typically, it's like 0.99. And so if my initial error is 1, the error after one step of value iteration is 0.99. the error after 2 steps is 0.99 squared. And I keep going like this and this, this and this, right? And this is like exactly the mathematical argument, the rigorous version. I've just like hand waved a bunch of stuff. Okay, properties of value iteration. Is it model-based or model-free? Hands up for model-based. Hands up for model-free. So it's model-based. Why is it model-based? It's model-based because in applying it, I need to take an expectation over transitions, right? And if I need to take an expectation over transitions, I need to know the dynamics or have an approximation to them. And if I need to know the dynamics, I'm model-based. Is it applicable to continuous or discrete state spaces or both? So hands up for only continuous, hands up for only discrete, hands up for both. So the answer is only discrete. Why? Because like I cannot apply this on a computer if there are infinitely many states, right? If there are infinitely many states, I can't apply this update rule, right? There need to be only finitely many state action pairs for me to actually apply this update rule. So value iteration is only applicable to finite state action spaces. Yeah, and also actions. Brilliant. We're now done. Thank you all very much for listening. Come chat to me if you have questions.